So now that we know the basic definition of differentiation, um, let's set up the tools that you have seen before in Calc 1 when you took it, that are the basic rules of differentiation, right? Theorem 1, let's start off with the easiest. If f is a constant function, then its derivative is 0. If f is a constant function, f of x is equal to c, then f prime of x is equal to 0 for every x. Proof. This is really easy. By definition, f prime of x is equal to limit h goes to 0, f of x plus h minus f of x over h is equal to limit h goes to 0, c minus c over h, which is equal to 0, right? So now we know that, if I take the derivative of a constant function, then it's 0. Theorem 2. If f is the identity function, which is if f of x is equal to x, then f prime of x is equal to 1. Proof. This is also really easy, right? F prime of x is equal to limit h goes to 0, f of x plus h minus f of x over h, which is equal to limit h goes to 0, x plus h minus x over h, these two cancel, which is equal to 1. Great. I have set up the base cases, more or less. Now, let us do some theorems which are slightly more non-trivial. Theorem 3. Let me just write these down all together. If f and g are differentiable at a, then everything nice holds true, which is f plus g prime at a is equal to f prime a plus g prime a. That is to say, f plus g is differentiable, f multiplied by g is differentiable, f multiplied by g prime at a. Well, everything nice holds true. This is not as nice. This is f prime a times g of a plus g prime a times f of a, right? 3. Well, if g prime of a is not equal to 0, then 1 over g prime of a is equal to negative g prime of a over g of a squared. And let's make a fourth case, which is combination of 3 and 4. That derivative of f over g prime at a is equal to f prime a g of a minus g prime a f of a all over g of a squared, right? So basically we are saying that f plus g is differentiable at a, f times g is differentiable at a, 1 over g is differentiable at a, and f over g is differentiable at a. Everything is nice. The derivatives might not look as nice, but things work out, right? Let us do proofs. You have seen these before, but this is mostly going to be a refresher. Proof 1. Limit h goes to 0, f of, f plus g of x plus h, not x plus h, a plus h, a plus h minus f plus g of a all over h. Well, this is equal to a limit h goes to 0 of f of a plus h plus g of a plus h minus f of a minus g of a all over h, which by definition is limit h goes to 0, f of a plus h minus f of a plus f of g plus h minus g of a all over h. Because I'm doing it very systematically, I'll write the next step also. F of a plus h minus f of a all over h plus limit h goes to 0. Oops. That should have been g of a plus h, not f of g plus h. G of a plus h minus g of a over h is equal to f prime of a plus g prime of a. Great. We managed to prove the first part. Second, now the derivative of product is slightly different, right? It's not exactly f prime times g prime. So we will have to be slightly sneaky about it. Prime at a is equal to limit h goes to 0, f times g at a plus h minus f times g at a all over h. Well, I can't simply do this nicely, right? Well, this is going to be f times f at a plus h times g at a plus h minus f at a times g at a over h, but this doesn't open up nicely. And so I have to use the trick that we often do whenever we have things like these which don't completely match, which is add and subtract a proper term, right? And so in this case, I am going to add and subtract minus f of a plus h times g of a plus f of a plus h times g of a. let me move this slightly, minus f of a times g of a all over h. Well, then this is limit h goes to 0. From the first two, I can pull out f of a plus h common. G of a plus h minus g of a over h plus limit h goes to 0. From the other two, I can pull g of a common. F of a plus h minus f of a all over h, which is equal to limit h goes to 0, f of a plus h times limit h goes to 0, g of a plus h minus g of a over h plus limit h goes to 0, g of a times limit h goes to 0, f of a plus h minus f of a over h, right? Because I can write these as product of limits if they exist. And I know individually all of these limits exist because my functions are continuous and differentiable at a. Great. Limit of f of a plus h as h goes to 0 is just f of a times, this is by definition g prime of a plus g of a times f prime of a, right? Or alternatively, this is f prime of a times g of a plus g prime of a times f of a. Whichever one you want to write it as, whatever makes you feel more comfortable. Either form is perfectly fine. Okay? That is number 2. Let us do number 3, which is if it's a fraction. Oops. 3. 1 over g prime of a is equal to limit h goes to 0, 1 over g of a plus h minus 1 over g of a all the way over h, right? Well, this is equal to my next line is equal to limit h goes to 0, 1 over g of a plus h minus 1 over g of a all the way over h, which is equal to limit h goes to 0, g of a minus g of a plus h over g of a times g of a plus h multiplied by h. Simplifying, this is limit h goes to 0, g of a minus g of a plus h over h multiplied by limit h goes to 0, 1 over g of a times g of a plus h, which, for my final coup de grace, is this is exactly equal to negative of g of a plus h minus g of a all the way over h times limit h goes to 0 as g of a is not 0. This is equal to 1 over g prime of a squared. Oops, not g prime of a. 1 over g of a squared. And so I get this is negative g prime of a over g of a squared. Finally, number 4, f over g prime at a well, I don't need to do this completely. I can do this as f times 1 over g prime at a, and then this by my rules 2 and 3. 2 is first f prime at a times 1 over g at a plus g prime at plus 1 over g prime at a times f of a, which is equal to f prime of a over g of a minus g prime of a over g of a squared times f of a, which, if I make my denominators equal, is f prime of a times g of a minus g prime of a times f of a all the way over g of a squared. Okay, that's my 4 initial rules.